Okay, so today I'm talking about three more functional groups that are related. They're going to be carboxylic acids, esters, and amides. Now, the esters and the amides are going to be derivatives of carboxylic acids, which means they come from carboxylic acid. So we're going to start with the carboxylic acid. So the functional group for carboxylic acids is going to be the carboxyl group, and it always comes at the end. So the general formula is carbon. Again, the R here represents the rest of the hydrocarbon chain, but here you're looking for the carboxyl group, which is COOH. That's a carbon double bonded to oxygen with a hydroxyl group on the side. So if you see this at the end or the beginning, okay, just remember that, it's okay, the end or the beginning of a carbon chain, it is a carboxylic acid. So how do we name carboxylic acids? Of course, we're going to locate the longest continuous chain that contains the carboxyl group. Remember, when we're looking at, hold on, I'm trying to let Ploy in. There we go. When we're looking at organic compounds, they are defined by certain things. So either a double bond, a triple bond, or a functional group. The functional group is always going to take the highest priority in identifying what the compound is. And it's also going to take priority in the numbering of the carbon chain. So instead of the alkane name, we're going to change the ending to oic acid. So methanoic acid, ethanoic acid, heptanoic acid, like that. If there's more than one carboxyl group, you're going to use the full name of the alkane and then add the suffix modified to indicate the number of carboxyl groups. So for example, dioic acid. So you might have something like ethane dioic acid or pentane trioic acid, like that. So here is methanoic acid. Again, one carbon is meth. You see that carboxyl group, that tells you it's a carboxylic acid. So you drop the E from methane, methanoic acid. This one, butanoic acid, because you've got 1, 2, 3, 4 carbons, which is bute. And again, it comes at the end. And here's ethane dioic acid. So you have 2 carbons here, and you've got 2 carboxyl groups. So then you keep the E from the methane, or from the alkane, ethane, and then you add dioic acid to show that there's a carboxylic acid at each end. So what are the properties and uses of carboxylic acids? They react to lose a hydrogen ion and they become negatively charged in water. So this hydrogen is easily lost because of the OH polarity. And so then you become a negative ion here and you release a hydrogen ion. This, by the way, is why it's an acid. If you remember back to last year when we talked about acids. So this hydrogen is extremely unstable and it's going to then react with water. Hold on, I'm trying to let ice in. Where's my, no. Oh, I'll just exit. There we go. So, oh my goodness, let me go back. No, not that either. Freaking hell. Okay. As I was saying, the reason why it's called an acid is because when it reacts with water, it loses the hydrogen here and becomes a negative ion. And that's the negative ion isn't what makes it an acid, it's this hydrogen here. So this hydrogen will then go to react with another water molecule because the hydrogen ion is extremely unstable and it will form hydronium. And that's why it's an acid, hence carboxylic acid, because this is a carboxyl group and it forms acid. Carboxylic acids are weaker than any inorganic acid. What do we mean by inorganic acid? That would be your sulfuric acid, nitric acid, what else? Hydrochloric acid, all of those, because they're not organic. This is an organic acid. Acetic acid is another carboxylic acid that's vinegar, or I should say it's the acid in vinegar. And if you remember the formula for acetic acid, it's CH3COOH. Look, there it is. So the IUPAC name for acetic acid is actually ethanoic acid. IUPAC stands for the International something of applied chemistry. I can't remember exactly what it is, but it is the the organization that is responsible for coming up with chemical nomenclature or systems for how we name things. Many carboxylic acids occur naturally in plants and animals. For example, citrus fruits contain citric acid. There is citric acid. It is a trioic acid. That's what gives oranges, lemons, and limes their sour flavor. Okay, and some other examples of carboxylic acids. We have methanoic acid, which is the acid that are in ants. So sometimes when an ant bites you, you have a reaction to that. That's from the methanoic acid. In rancid butter or rotten butter, it produces butanoic acid. Milk, fats, coconut oil, and palm oil contain hexanoic acid. You can see here there's 1, 2, 3, 4, 5, 6. 6 is hex, got that carboxyl group at the end. Sour milk, blood, and muscle fluid contains lactic acid. Malic acid is in apples, and there's a vegetable called rhubarb, which is a very sour. They make pies out of it, and that contains oxalic acid. And this is not an IUPAC name. This is like an acetic acid type of name. It's not the systematic name for the compound. Carboxylic acids are also used as food additives. Ethanoic and citric acids. Ethanoic, remember, is vinegar. That's this is the IUPAC name for acetic acid. And citric acids are used in in foods to give them a tart or acidic sour flavor. Benzoic, propanoic, and sorbic acids are used as preservatives. So a preservative is a chemical that's going to extend the shelf life of a food product. So that like when you go to 7 and you want to buy a sandwich and it can sit there for like weeks and not get moldy, those are preservatives. All 3 of those acids kill bacteria that make your food spoil, and so it makes the food last longer on the shelf. The most widely used carboxylic acids are methanoic and ethanoic. They can be made cheaply. They're also used as starting materials for many chemical processes. Ethanoic acid is used in the production of polyvinyl acetate, or PVA. This is used in latex paint, adhesives, and textile coatings. I do believe that is also used in TOA, the glue. That's like I think that's a latex glue. Okay, now we get to esters. Now, esters are basically if you take carboxylic acid and the hydrogen from the hydroxyl group is replaced by an alkyl group. So the general formula here, again, this is our original carboxylic acid, but we have removed the hydrogen and we've replaced it with an alkyl group. So the alkyl group, of course, will depend on how many carbons are on the other side of that oxygen. So in naming esters, we name the carboxylic acid from which the ester was formed. We're going to change the oic acid ending to O8. Okay, so this is the first time that we have an ending that's not really reflected by the name of the compound, right? So because we had alcohols, the name ends with OL, alcohol, and it's like ethanol, methanol, butanol. Aldehydes end with al. Ketones end with one. The carboxylic acid ends with oic acid, but this time the ending, there's no real relation to the group name. So this gives the second half of the esters name, because remember, we have an alkyl group on the other side of that oxygen. Then we're going to identify and name the alkyl group that has replaced the hydrogen of the hydroxyl group. So this is going to be really important for you to identify the parent chain that goes up to the carboxyl group at the end. And then it's important that the alkyl group that you identify is what comes after that single bonded oxygen at the end of the chain. There should be a space between the name of the alkyl group and the name of the parent compound. So for this one, you identify your former carboxyl group, and then the first part of this becomes the second part of your name. So that has 2 carbons. So that's F. And so we're going to change it to ethanoate, because it would have been ethanoic acid. And then on the other side, you see here's where the single bonded oxygen is. So that means that this is the alkyl group. This 2-carbon chain has replaced the hydrogen that used to be at the end of that. So that's your alkyl group. And again, 2 carbons is ethyl. So ethyl space ethanoate. Okay, and then this one again, you have first identify where the carboxyl group is, and then everything on the carbon side of that is part of the parent. So you count, let's see if I can undo my writing. Okay, so this is where the carboxyl group is. This is where the oxygen is. So this is the alkyl group. And if you want to, you can start by naming that first, because you can identify that first. So that's ethyl. And then you count 1, 2, 3, 4. 4 is bute. So that's butanoate, ethyl butanoate. Properties and uses of esters. These are common in plants. They are also responsible for some distinctive flavors and odors. So here we've got ethyl butanoate, which is the pineapple flavor. Methyl salicylate is wintergreen oil. We have geranyl formate, or geraniol, whatever, formate, which gives rose its scent. Grape juice and jasmine come from methyl anthranilate. Don't know if I'm pronouncing that right, but it doesn't really matter. And lavender is linalyl acetate. So it's kind of similar to the aldehydes and ketones, which are also responsible for certain flavors and odors as well. Chemists have learned how to synthesize these and many other naturally occurring compounds to use as food additives. So this is where we get the extracts from. We have imitation banana extract because we can copy the carboxylic acid that gives bananas its flavor, and then we synthesize it in the lab. And that comes from isoamyl acetate. And that's used as artificial flavoring. And finally, we have amides. Now, amides is where the entire hydroxyl group is replaced by an amine group, which is NH2. So if you see double bond O and then you've got an NH2 at the end, that is an amide. And of course, looking at the structure here and then how you name it. So if you see double bond O sticking up and a nitrogen at the end, again, of course, because it comes at the end, that's where the carboxyl group used to be. Then you count, here's 1, 2, 3. and you just have the alkane name without the E, and then you add amide at the end. So this is propanamide. Same thing here. And again, when it comes to position numbers, you're going to count this as number 1. Same with the aldehydes like we did before. So you identify this as being an amide. You're going to count how many carbons are in the parent compound. So 1, 2, 3, 4 is bute. So that's butanamide. And then you identify your alkyl group here, which is bromo. And it's on number 1, 2, 2-bromobutanamide. Now we've got different kinds of amides. So this is a primary amide. And you count 1, 2, 3, 4, 5. 5 is pent. So this is pentanamide. That's not correct. It should be pentanamide. Although maybe you see pentamide, I don't know, but I think it should be pentanamide. Now, a secondary amide is when you start replacing the hydrogens on the other side of the amine group. And so you're going to have 1, 2, 3 is prop. So propanamide. And then you just add the name of the alkyl group, methyl. So because it's an amide, that means that the methyl group has to come on the other side of the nitrogen, because this is what identifies it as an amide. So it's methylpropanamide. When you name it, you use an uppercase N to designate that the alkyl group is on the nitrogen atom. That's correct, because I could have, say, like another methyl group here. So that's an important distinction. Why is it? Oh, there we go. Whoop, 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 whoop. There we go. So this is N-methylpropanamide. So this is a really important part of it. If I say methylpropanamide, that could be O, and then NH2, and then if I put CH3 here, that would be methylpropanamide. Not N-methylpropanamide. So that's an important step. Now, the last kind of amide is called a tertiary amide because you have replaced both of the hydrogens, and you name it the same way. You have to identify by using uppercase N to indicate where the alkyl groups are. So if you have NN dimethylpropanamide, that means that you've replaced both of the hydrogens from the amine group, with a methyl group. Amides are used widely in industry. They're found in plastic and rubber, paper, water and sewage treatment, and color. They're in crayons, pencils, and inks. Okay. Let me